Hello, my name is Jeongbeen Yoon at POSTECH, South Korea. I will present our work Semi-supervised domain adaptation via sample-to-sample self-distillation. This work is jointly done with Dahyun Kang and Minsu Cho. The goal of semi-supervised domain adaptation is to adapt a model on the target domain with a few labels of target data. SSDA renders the adaptation problem more practical because we are often able to get additional labels easily. However, SSDA suffers from its two main issues. The main issue of general domain adaptation is the intra-domain discrepancy, which is the gap between the source and the target distributions. Furthermore, in SSDA, intra-domain discrepancy occurs because of the additional labeled target samples. Previous methods for SSDA aims to address the issues using a prototype-based approach. In this presentation, we propose sample-to-sample self-distillation that leverages rich sample-to-sample relations. We can observe both inter- and intra-domain discrepancies in Figure A. Then in Figure B, we generate assistant features to bridge the domain gap. Inspired the fact that the domain and the style of an image are closely related and training with mixed style features helps to bridge the domain gap, the assistant features are created by transferring intermediate styles between the teacher and the student. In Figure C, the assistant features are used. Then, the adaptation result is shown in Figure D. Now, let me introduce our method in more detail. This figure describes the overview of our method. It achieves the goal by alternating two steps, the student set generation step and the training step. The training step consists of sample pairing, assistant generation, and self-distillation. We will explain each step in more detail. Reliable student set generation step consists of pseudo-labeling and reliability evaluation. We assign a class label y hat to each unlabeled target sample x prime. Then we drop unreliable samples according to the two conditions in the equation, because pseudo-labeling is not perfect. In this way, the model assigns pseudo-labels to confident samples so that the model can take reliable pairs. After obtaining student set, we construct a pair of a labeled sample and a pseudo-labeled sample. After pairing a teacher and a student sample, an assistant feature is generated by an assistant generation module, which transfers an intermediate style of the teacher and the student. The content of the assistant follows the content of the student. To blend the style of the pair, we construct new style statistics, mean and standard deviation, by interpolating between the style statistics of the teacher and the student. There are three training objectives for our network. Cross-entropy loss is calculated with teacher samples and their ground truth. Pair loss is calculated with the predictions of teachers and students. It effectively reduces both inter- and intra-domain discrepancy. We additionally include weighted cross-entropy loss calculated with students and pseudo-labels. I will present several experiments briefly. This table shows the classification accuracy on the DomainNet dataset. S3D achieves higher accuracy than the previous methods in most domain adaptation scenarios. We also examine our method with increasing target labels per class by plotting the graph on the left. S3D consistently outperforms current state-of-the-art along with the increasing number of target domain ground truths. For visualizing the inter- and intra-domain discrepancies, the right two histograms plot cosine similarity between teacher and student embeddings from the same class. The figure represents our method gradually alleviate both discrepancies. This is our summary, and thank you for watching.